Hello everyone, this is lecture 4 of course PE 645. In today's lecture we are going to deal with the gray level run length matrix, or in short GLRLM. GLRLM is a tool used in image processing, especially for texture analysis. This tool or technique focuses on counting the number of gray level runs of different lenses in an image. It's a type of the second order features. And as mentioned in the previous lecture, second order features tries to find the relationships between the neighboring pixels. So in GLRLM, a gray level run is defined as a sequence of consecutive collinear pixels sharing the same gray level value. To further understand this, consider an example where an image consists of different gray levels, and when we scan the image in a specified direction, such as horizontally or at an angle of 45, we count how many times we encounter sequences of pixels or runs that have the same gray level value. For example, in a specific direction, for example horizontally, we will try to find how many pixels with the gray level of 5 cascaded together. So if we find it to be 4 times, then the run here will be 4. Another example, if we find a sequence of 4 pixels in a row, all having the gray level value of 3, then the run will be 3, and this value will be recorded in the gray level run length matrix. The gray level run length matrix will take a symbol of M, and it requires 3 parameters to facilitate its calculations. The angle, and this angle refers to the direction of analysis, where we count how many times we encounter sequences of pixels or runs that have the same gray level value. It can be 45, it can be horizontal, it can be vertical. It depends on which direction you need. Second, the number of gray levels, which is N. This parameter indicates the number of discrete intensity levels present in the image. So we can say in that image we have 255 gray levels. So N in this case will be 255. Third, maximum length, which is R. This parameter represents the number of columns or the width in the image, and we can determine R practically as the maximum value between the width and the height of an image. And you are selecting between the maximum of them because some images are with non-equal dimensions. So now the 3 parameters are theta, N, and R. So how to calculate the GLRLM matrix? We will define 3 parameters depending on the problem and the image in hand. So this is our image. In that image we can determine the value of N and the value of R. N will be the count of the unique values, or we can get the maximum number in that image and add 1, similar to what we did with the GLCM matrix. So the maximum number here is 3, so 3 plus 1 will be 4. So N in that case will be 4. And R will be the maximum between the width and the height. So we have 5 rows, 5 columns, so R will be 5. And let's define theta equals to 0. So 0 means we are moving horizontally from left to right. The next step is to create an empty array, an empty matrix with dimensions n multiplied by R. For the rows, we will define the gray levels, and for the columns, we will define the runs. So in that case, the dimensions will be 4 by 5. The rows will start from 0 up to the maximum intensity or gray level, which is 3, and the runs will start from 1 until we reach the value of R. And similar to GLCM, we can take that reference to determine in which direction do we go, and the commonly used thetas are 0, 45, 90, and 135. Similar to GLCM, we can use these 2 formulas to determine the next or the neighbor pixel, but in that case, in GLRLM, we will set the D value to be 1. So the formula will be x target will equal to x current plus the rounding of cosine theta, and the same for y target, but using negative rounded sine theta. So if theta is equal to 45 and our position now is 1 and 1, which is here, by calculating cosine theta and sine theta, we can get x and y to be 2 and 0, which will be that position. And if theta is equal to 90, and by substituting in the same formulas, but assuming d equals to 1, we can get the next position of the position 2 and 2 will be 2 and 1. So if you are here, you will move in that direction. In GLCM, we only got the next neighboring pixel, but in GLRLM, we need to find the run lengths. And this means we need to find all neighboring pixel in a specific direction. So if we are in theta equals to 0, and we will go in the horizontal direction from left to right, so to find the run lengths, we will find all neighboring pixels in that direction. So for example, if you are here, you move that direction until the end. If you are here, you move that direction until the end. And if you are here in the fourth row, you will say that 1 is repeated 3 times. So you will fill the table as we are going to see after a bit, that the value of the run here will be 3 and the value of the run here is 2, because 1 is repeated 3 times and 2 is repeated 2 times. And for theta equals to 90, you will move the direction. So if you are here, you will move in that direction to get all of the next pixels. And if theta equals to 45, you will go that direction. And if theta equal to 135, you will go in that direction. So after initiating the run length matrix with initial value of zeros and understood the directions of thetas where to go based on the theta value, so we need to solve our task. As we mentioned, theta equals to 0, we move the direction. So we will loop on a row by row and count the number of runs based on each pixel. And if pixel is counted or seen, we will skip it or ignore. So let's start. 1 here is repeated once in a consecutive collinear manner because there are no ones next to it, as the next number is 2. So the gray level 1 is repeated once. So we go at the gray level of 1 and increment that field to B1. And for 2, the next pixel, it's repeated once or has a run of 1 because the next pixel is not equal to it. So we will go to the field of gray 2 and add 1. And similar to 3 is repeated 1 or has a run of 1, we will add 1. 2 has a run of 1, so we will increment that field to be 2, and the same for 1, this field will be 2. We will do the same for the next row. 3 is repeated once, and the same for 1, 2, 1, and 0. So let's go to the third row because we will encounter a run of 2. This is repeated once, so we will add 1 to gray 0, and this is repeated once. We will add to gray level 3 1, so it will equal to 3. And for 2, we will find that there is another neighboring pixel with the same value. So in that case, 2 has a run of 2. So we will go to gray of 2, run of 2, and increment that field by 1. Next, 1 is repeated once. We will increase that field by 1. For the next row, 1 is repeated 3 times because there are 3 consecutive ones in that row or that direction. So we will go to gray 1, run of 3, and increment that field by 1. And for 2, this is a run of 2, so we'll go to gray 2 and increment that field of run 2 by 1. And the same for the last row. So the final run length matrix will be like that, and empty fields will be zeros. So how can we write a script that can handle the different directions based on theta, not only the horizontal direction, and be able to generate the run length matrix? Simply, we will create in the code an empty Boolean matrix that looks like that matrix, which will be similar in dimensions to the original image or the original matrix. And during our loop on the pixels in a specific direction based on the two formulas, each pixel that is counted once will enforce that table to change its flag from false to true, so we cannot count that pixel again. So for example, if you are here and we have a horizontal direction, so we will find all of the next pixels which are similar to that number, and create a counter that counts the number of occurrences until we reach a pixel which is not the same as that pixel. So we are at one gray level. We will check the next level. It's 1, so we will increment the counter to be 2 and check the next one. It's equal to 1, which is equal to our current pixel, so we will increment the count to be 3. Then we will check the next pixel, which is not 1, so we will stop. So the count here is 3, so the run length matrix will go to field 1 and run of 3 and increment that field. And concurrently, on each pixel that incremented the counter, will change the flag to true. So we counted 3 times for these 3 pixels. We will change the flag to be true. After we finish that pixel, we will move to the next pixel, which is here. By checking the seen matrix, we will find that field is seen already. So we will skip that field. We will move to the next pixel. It's also seen, so we'll ignore it. So we'll move to the next pixel, which is here, and we will do the same. This method is helpful especially if we are dealing with the directions 45 and 135, which are these directions. So to understand it programmatically, let's go to the code. We have created the array and defined theta equals to 0. We calculated the n and r. N equal to the max of a plus 1, and a here is the matrix. R will be the maximum of the shape. We have 5 by 5, so R will be 5. Then we created a run length matrix of dimensions n by r and scene matrix, which will be the same shape of the matrix A. Then we define the directions of each pixel, dx and dy, which will be rounded cosine and rounded sine of theta. Then, as we mentioned, we will loop on each pixel in the matrix, and for each pixel we will check first if the pixel is already seen or not. If seen, we will skip it. So as we did, we checked that pixel, it's seen, so we skipped it. Next, if the pixel is not seen, we will do the rest of the code. First, we will convert the flag of it from unseen to seen and get the current pixel, so we can do the comparison between current pixel and the next pixels. And we will set the counter to be 1, or the distance, or the current distance to be 1, and d here is the counter that will be used later to increment a value of 1 in the run length matrix. And we created a loop here to loop in the direction we are going and count how many pixels that equal to our current pixel. So first we set a condition here in the while loop that we only need to work in the boundaries of the image. So if I in the boundaries of top and bottom of the image and j from left to right, you can do what's going here. Here you checked that the next pixel at a specific distance from the current pixel is equal to that pixel or not. If so, you will set that pixel also to be seen and increment the value of d by 1. Otherwise, if you encountered any pixel that's not equal to the current pixel, you break the loop, which is the while loop. Then the value of d will be the value of the run length. So you go to the run length of the current pixel and the d value and increment 1. And you are subtracting 1 here because, as we mentioned, the indexing in Python starts from 0. And here in our implementation, mathematically, we started from 1. So we need to decrease the value of d by 1 to get the correct index. After that, you are printing the run length matrix. If you executed the code, it will print the original matrix and the run length matrix. And to validate your code to be running correctly or not, you can calculate it manually and validate it with the code. So in our case, they are getting the same results. After getting the run length matrix and computing it, we can get a set of statistical measures from that matrix, which are related to the GLRLM. These features measure various statistical properties of the gray level runs, and this will help to characterize the texture more comprehensively. First, the features are short run invasive or SRE. This measures the distribution of short runs in the image, and it's sensitive to the presence of short runs of pixels with similar gray levels. Long run invasive or LRE, it's the same but for the long runs. It measures the distribution of long runs in the image, and it highlights the presence of long runs of pixels with the same gray level. Gray level non-uniformity, GLN. It measures the similarity of gray levels in the image. A lower value indicates more uniformity in gray levels, and vice versa. Run length non-uniformity or RLN. It measures the uniformity of run lengths. A lower value indicates more uniform run lengths throughout the image. Run percentage, RP. It indicates the percentage of runs relative to the total number of pixels in the image, so it can provide a measure of texture complexity. Low gray level or LGRE. It focuses on the distribution of low gray level values. High gray level, HGRE. It's similar but for high gray levels, so it concentrates on the distribution of high gray level values. It's higher when high gray level values form longer runs. So now we have 4 plus 3, 7 features that can be calculated using the run length matrix. And these are the corresponding formulas. For example, the SRE, you are looping on each element in the run length matrix, and here we defined R as the maximum run length, and G, which is in our case equals to N, and the value of P is the normalized version of the run length matrix. So after getting the run length matrix, you divide it by the sum of the numbers in that matrix to normalize it. And for each value or for each normalized value, you divide it by J squared, and J here is the index of run length. So if you want to throw that formula on each pixel, in our example, you will divide 3 by 1 square, 6 by 1 square, 3 by 1 square, 4 by 1 square, 3 by 2 square, and 1 by 3 square. You sum all of these numbers and divide it by 20, and that value is the sum of all numbers in the run length. And in the formula, which is represented here, try to distinguish between G and N. G in our code is represented by the N value, which we calculated earlier, and N here in the formula will be represented by the sum of the run length. And to calculate the sum, you sum all of the numbers in the run length matrix, that will get 20. So the SRE value will be approximately 0.84. And for LRE, you are doing the same, but instead of the division, you are doing multiplication. So you multiply 3 by 1 square, 6 by 1 square, 3 by 1 square, 4 by 1 square, 3 by 2 square, 1 by 3 square. You sum all of these numbers and divide it by 20. You will get 1.85. And for HGRE, if you notice, here we are multiplying by J, which is the index of the R loop or the run length, which is represented here. And for that formula, we are multiplying by I, which is the gray level indices. So we multiply 3 by 1 square, 6 by 2 square, 3 by 3 square, 4 by 4 square, 3 by 3 square, 1 by 2 square, and you sum all of these numbers and divide it by 20. So it will get 7.45. And just to notice, we multiplied, for example, 3 here by 3 squares because the counting here starts from 1, but we here started from 0. So you can write 1, 2, 3, 4 and start to do the multiplication. So how to code all of these features together using Python? We use the same code to calculate the GLRLM, and we denoted the N in the formulas to be RLN, run length sum, which is equal to the sum of the run length after calculating it. And then we calculated the different features from here to here. So for example, short run in phases, we use the matrix operations from the NumPy by simply instead of using loops to make it more time efficient and faster. So how we did that? We simply in the SRE wants to divide each element by the run length counter. So for example, 3 here is divided by 1 square, 3 here divided by 2 square, 1 here is divided by 3 square. So simply we can divide each row by a counter from 1 to 5 square. So we can get each row divided by 1 to 5, and by doing that using matrices, it will get another matrix that we can sum together to get that value. So for example, if the matrix is represented here and we have a vector from 1 to 5, it will be divided. This vector will be divided by each row. By doing that, it will get another matrix where each element is simply the original element divided by the corresponding run length value squared. So by doing that, we will need to sum all of these numbers together and then divide it by 20 or n in the formula. So what we did here is what we mentioned. We got the matrix, divided it by a vector squared from 1 to r plus 1, and r here is the maximum, which is 5, plus 1 is 6, so from 1 to 6, and the function nb dot arrange will get the count from 1 to 6, and 6 is not included, so it will be a vector 1, 2, 3, and 5. So by doing that, we are getting another matrix, but divided by the corresponding run lengths. So we are applying the summation and then dividing by the run length sum. We will do the same for others. For example, LRE, instead of the division, we are applying multiplication. What about GLN or gray level non-uniformity? Here it squares the summation of each column in a specific row. So if you have a matrix here, it will sum all of these numbers and square that, and then apply the same for here, and then calculate the total summation and divide it by 20 or the any value. So to do it programmatically, you can square the summation of the matrix, and you can use axis of 1 to access the columns and generate a matrix of rows. So simply there is a matrix here of 3 rows and 4 columns. For example, by applying axis of 1, it will generate a vertical vector like that, where each value here represents an operation applied on the columns of a specific row. So by doing that, we will need then to sum all of these numbers as we did here. Then we divide it by the RLN summation. For RLN, it's same, but instead of summing the columns, we will sum the rows. As you see here, the two loops are swapped. So instead of axis of 1, we will get axis of 0. And this means if we have a matrix of 3 rows and 4 columns, it will generate a horizontal vector of 4 values, where each value here will be an operation done on a set of rows in a specific column. So we need then to sum this vector as we did here. For the run percentage, we divide the value of n, which is calculated by the variable RLN, by the total number of pixels in the image, which will be the product of the shape. So if we have 5 by 5 image, as in our example, the total number of pixels in our image or matrix will be 25. And for the low gray level run in phases and high gray level run in phases, it's similar to SRE and LRE, but instead of dividing and multiplying by j, we here dividing and multiplying by I. So here in SRE and LRE, we made a range from 1 to r plus 1. Here in LGRE and HGRE, we made a vector from 1 to n plus 1. And we added that portion here and here so that the NumPy can understand that we are doing matrix multiplication. Finally, we printed different features such as SRE and LRE for the corresponding matrix. By running the code, we will get these values. And you can also validate your results with calculated ones. For example, the long run in phases is 1.85, which we calculated here. And for HGRE, we calculated 7.45, which is here. Next, we need to replace the matrix. Instead of applying a matrix 5 by 5, we need to apply the features and run length matrix on an image. As we did in GLCM, we have an image, we have a mask. We need to bitwise and both of them together and get the ROI, remove the black region around it, and get the ROI variable, and use that variable instead of the matrix to get the run length matrix and features. So in that code, we encapsulated the calculation of run length matrix in a function, and if you open that, you'll find it's similar to what we illustrated, but we added if we need to ignore zeros and is normal, similar to GLCM, and removed the distance from our equations. So if you need to normalize, which is default true, you will divide the matrix by its summation. And if you need to ignore zeros, which is also default by true, so you will check before incrementing the run length matrix. If you need to ignore the zeros and the current pixel is 0, then you need to continue. And we didn't add this part here, for example, or here at the beginning of each pixel, because we need the pixel to be flagged in the same matrix to be true, to avoid looping on them multiple times, to reduce the time consumption. And we also added a function, calculate GLRLM features, and we encapsulated all of the features in that function, and this function returns a dictionary similar to GLCM code, and this dictionary contains the keys and values that are calculated. The change here that we replaced the A matrix by our ROI, so we read the two images, the image and the mask, applied bitwise between them, grouped the ROI, and removed any bounding regions of zeros, and then we used that instead of the A matrix, applied it to that function, got the RLM matrix, used that matrix to calculate the features. We got the features and printed them. And these are the corresponding results. You can also change theta value and check your results. Then we need to apply our matrix and features on a 3D volume, which consists of a set of slices. And similar to GLCM, where we calculated the XYZ new equations in 3 dimensions based on the spherical coordinates, and we got these 3 formulas, but in our case we removed the d or substituted it by 1, but kept the cosine and the sine similar to GLCM. And then if theta equals to phi, we can reach the final 3 formulas that will be here. X will be x current plus rounding of cosine theta multiplied by sine theta, and y will be y minus rounding of sine theta square. Z will equal to z plus round of cosine theta. And as we mentioned in the previous lecture, we need to apply padding for each slice in the volume to unify the shapes, because when we grouped each of these slices, they got different dimensions, for example here and here, and if we applied that without padding, it will raise an exception. So what we did here, we used the same read volume function from the GLCM code that loops on the different slices in the image and create a volume variable, and updated our GLRM 2 functions to be from 2D to 3D with the same parameters. So here what we changed is dx, dy, dz to be the new equations, and added a new loop for the z-axis, and instead of accessing I and j, we are accessing I, j, and k, and instead of only 4 conditions for top, bottom, left, and right, we added a new dimension for x, y, z. And for the 3D features, because the run length matrix is only 2D, we kept the function as it is. If you notice here, the run length matrix is equal to n multiplied by r. N represents the gray levels, whether it's a 2D or 3D, and r is the number of run lengths, which will be the maximum of the shape of the volume, which direction is the maximum. Then we defined the image and segmentation paths for 3 slices, defined theta, read the volume, calculated the run length matrix, and then calculated the features and printed GLRLM features. If we executed the code, we will get these results. So what we did in this lecture looks like what we did in the GLCM, but the differences are how to calculate the co-occurrence matrix regarding GLCM and how to calculate run length matrix regarding GLRLM. And second, based on the co-occurrence matrix, we could calculate specific features such as correlation, entropy, and dissimilarity. And based on the run length matrix, we could calculate short run and long run in phases. We applied both of them, GLCM and GLRLM, on images and volumes. Third, you may notice that the GLCM in 3D may take longer than GLRLM 3D because in GLCM we added a new dimension to the co-occurrence matrix, while for the run length matrix we used the same 2D because the run length depended on the gray levels and maximum number of run lengths.